Alright, here's another solution stoic problem. This one sounds a little bit different. It says that 15 milliliters of a 1 molar potassium iodide solution, SOLN stands for solution, reacts with 20 mils of a 6 molar lead 4 nitrate solution. Calculate the concentration of potassium and lead 4 in the supernatant. So this one doesn't ask me for the mass of solid produced. But since I still have these two substances reacting, I still need a balanced chemical equation. In order to calculate the concentrations of these two ions, I need to know whether or not the amounts of those ions change through the course of this reaction. So let's see. Potassium iodide reacting with, lead 4 nitrate to produce lead 4 iodide and potassium nitrate. So here's my solid that I'm creating, but again, they didn't ask me to calculate the amount of that solid, so that's about as far as he's going to go. Let's see if I can balance this real quick. There we are. So now let's come up with our complete ionic equation to figure out which ion concentrations change from left to right and which ones do not. Potassium iodide is soluble, so I can break it apart into its ions. Lead nitrate, courtesy of that nitrate, is also soluble, and I can break it apart into its ions. Since lead iodide is solid, it has to stay put, and potassium nitrate, also soluble. Okay, there we have it. So notice my potassium does not change from left to right. It will not be part of my net ionic equation, which means that the amount of potassium I start with is going to be the amount of potassium that I end with. So this calculation should be pretty simple. All we're going to worry about is this bit right here. So I know I have 15 milliliters of that potassium iodide solution, and if you remember from our last video, I can use this molarity right here as a ready-made conversion factor between a volume unit and a counting unit like moles. But that volume unit has to be liters. This milliliters, not going to cut it. So the first thing I have to do is convert from milliliters to liters. Got that all set. Then we use our molarity here to get me from liters of potassium iodide to moles of potassium iodide. I'm going to go ahead and write in one more step here, just for the sake of demonstration. Notice it doesn't ask me for the concentration of potassium iodide, but just of potassium ion. So if we look at this compound here, for every 1 mole of potassium iodide, I have 1 mole of potassium iodide. Since this is, 1 mole of potassium ion. Since this is a 1-to-1 relationship, this step is not vital to the calculation. But I wanted to go ahead and point it out, just because if we had K2O or something like that, this would not be a 1. So be careful to look at your compound before you complete out this moles of ion calculation here. So we have 15 divided by 1,000. This is how many moles of potassium ion I have present. When they ask for concentration, they're asking for molarity, which we've already said is moles per liter. Now this is not just any liter, but this is going to be total liters because we're looking at the supernatant. This is the liquid on top of our solid product. So that means I'm going to have to add together my 15 mils of potassium iodide and my 20 mils of my lead 4 nitrate. So 15 plus 20 is 35 divided by 1,000. There we are. So 0.015 divided by 0.035 gives us a 0.4. How many sig figs can I have? 2. 0.43 molar solution of potassium iodide. Potassium. Why do I keep doing that? Yeah, goofball. Make sure that you have number, unit, and thing in that final answer. So, first one, check. But they also asked me for the concentration of lead 4 in my supernatant. Notice my lead 4 is going to change. On the left, lead 4 is by itself. On the right, it's in the solid. So this means that some of my lead, if not all, has been used up, but I need to find out whether or not my lead is the limiting reagent. So guess what? We end up having to do solution stoich anyway. So off we go. I'm going to skip the map part. There are previous videos that will walk you through mapping out exactly which conversion factors you are going to use. For the sake of time, I'm going to skip that step and jump straight to the numbers. Milliliters are no good. Let's see, there's a 4 in front of there. A 1 in front of there. I'm actually going to stop at moles here just for the ease of my own calculations. So 15 divided by 4,000. Now let's go ahead and do our other reagent. Let's see, that is a 6 molar lead nitrate solution. Not 3, goofball. 1 to 1. Oh, that's nice. So 20 times 6 divided by 1,000 is a 0.12 moles of our lead iodide. Alright, so looks like it is our iodide that runs out first. This gives me the smaller number of moles, which makes my limiting reagent my potassium iodide, not my lead nitrate. This means that I will in fact have excuse me, I will in fact have lead ions left over floating around in my solution. So I need to know just how many lead ions from this lead nitrate am I going to use to make this substance here. Well, if we look at this, we notice that for every 1 mole of lead iodide, I have 1 mole of lead ion. So if I make 0.0037 moles of lead iodide, that means I needed to have 0.00375 moles of lead 4 ion in order to make that. So let's see just how many moles of lead I started with. So I'm going to take this conversion right here. Okay, actually that's a 1 to 1. I'll calculate it out for you anyway on a separate set of boxes. So for every 1 mole of that lead 4 nitrate, I get 1 mole of lead 4 ion. So I started off with 0.12 moles of that lead ion. I'm going to use up 0.00375 moles of that lead lead 4. And again, I can tell that because this is a 1 to 4 relationship between my lead and my iodide. So it takes 4 times as much iodide to make this molecule here. So this is how much I started with, and I'm going to subtract how much I actually used, which was not much. So this is how much lead 4 I still have floating around in my solution. In order to calculate the concentration of lead left over, I have to find the molarity, which is, as you well know by this juncture, moles per liter. We just found the moles. Divided by, this is total liters again, since we're looking at the supernatant. I already found my total liters up here when I added together my 15 milliliters plus my 20. 3.32 molar lead 4 solution. So there's a lot more lead left in this thing than potassium. How interesting. So that's another direction that these ion concentration problems can take. If this was confusing in any way, let me know in the comments box so that I can put up another example. Best of luck.